Alright, so in this tutorial we're going to revisit the idea of gravitational potential energy, where you're going to transform the very simple mgy equation into a more universal one. The reason for this is if we want to calculate potential energy as we get further and further away from the Earth, well, y would go up, but g is not going to stay the same. It's going to change. So we got to come up with a more universal equation for gravitational potential energy. So it's going to kind of take a weird turn to it. We're going to introduce a concept that is, on one hand, not too difficult, but it's not obvious. So you want to pay close attention to the details of this, and then we'll do a bunch of application. During the tutorial, do one or two, and then you'll have the rest on your own to practice. Okay, so another question we could ask from the MGY is what happens to the potential energy as we get further and further from a planet. Okay, so again, if we have what we've learned so far, it's mgy, we see that ug is proportional to y, so as y goes up, is this going to approach infinity? Okay, does it make sense that if you are, have a really large distance from the planet Earth, you're going to have an infinite or approaching an infinite potential energy? And in a word, the answer is no. Okay, there's a few reasons why that doesn't make sense. And one I've alluded to already, and that's the value of g is dropping. Okay, and that's what we have here. If we remember from our universal gravitational, the force of gravity between any two objects falls off by the square of their distance. So as we approach infinity, okay, and it doesn't have to be infinitely far away. We're just talking like, 10 to the 8th, 10 to the 9th, 10 to the 10th meters. Okay, as it approaches that, the value of gravity approaches 0. Okay, and if the value of gravity approaches 0, then it doesn't really make sense to talk about potential energy. Okay, so it makes sense that the amount of potential energy gravitation would also approach 0 as we get further and further away, which contradicts the MGY idea. Okay, now a little bit more subtle aspect as to why this wouldn't make sense for potential energy to approach infinity is that we would expect that objects would have less potential energy the closer they are to one another, because the force between them is attractive. Okay, in other words, if you have two bodies that are attracting one another, they want to be near each other, so to separate them would be kind of like stretching a spring. You'd expect the potential energy to go up and up and up the further away they are. Okay, which contradicts this idea that gravity or the potential energy would approach 0 as it gets further and further away. Okay, so how do we get around this? Well, I'm going to give you an analogy before I come back to the equation here. Okay, and this is kind of the Einsteinian view of gravity. I think it makes it easiest to look at. And that is, suppose there is just empty space and there's no mass in it. Okay, and so we would say the mass would be flat. I'm going to draw it like that. So here we are sitting in there, and there is nothing going on along this flat line. And then we introduce a large mass to space-time. And as we mentioned back in the day, when we introduce a large mass, we kind of warp space around it as kind of represented by that little hole there. So what you need to think of, and this is the easiest way to understand what we're about to show mathematically, is let's say you're standing somewhere on the Earth. Because the Earth has warped space-time, in a sense, it's created a hole in space-time, okay? Or the fancier term is a potential well, okay? Like a water well, okay? So what you have is, if you take this as your baseline, normal space, and that's really what we mean at infinity. That's one way you can look at this infinity. Your potential energy would be 0 there, okay? That's just normal. So when you go into the well, the deeper the well, the more negative you're going to have. So we have a negative UG by virtue of being in there. Okay, and so that's one of the solutions to how we get around this, the points that were brought up earlier, is that if you are on a surface, okay, the closer you are to it, the more negative it is. So technically it's the bigger the negative value, the lesser the lesser it is, right? We learned from a mathematical standpoint that negative 20 is less than negative 10, which is less than 0. So we're going to take that approach. And if you want to escape the well, the idea is you want to have 0 potential energy. So it would be 0 at infinity, and it gets more and more negative the deeper in the well you have. Okay, so cogitate out a little bit because we have to reflect that in our equation. So let me go back to what we have here. I'm not going to do the derivation because it requires calculus, okay? But the universal form of gravitational potential energy is, first of all, it's going to be negative. And that's really, really important. So if you are at infinity from any body, you have 0. And then as you get closer and closer to that body, it becomes more and more negative. And it takes on the equation negative g m little m all over r. All right, this looks very, very familiar to us. If you go up a little bit further on this tutorial, we see it's very similar to our force of gravity equation. That doesn't have a negative in it, and there's a square in there. So you're going to be very careful not to confuse the two. So we see that the gravitational potential depends on the mass of the object that's brought in it, the mass of the planet, big G plays a role, and then we have the R. And that negative simply means the closer we are to the body, the smaller it is. So this graph kind of reflects that. We see, forget about this part here, won't worry about it. We have an inverse, but it's, if you will, an upside down inverse. So if R represents the surface of the planet you're on, you are at the most negative value, okay? And it's very, very high. And then as you get further and further away from the planet, you follow this trajectory, if you will, and we approach the asymptote of 0, okay? So to have 0 potential energy, for all intents, you don't have to be literally infinitely far away, but just really, really far away compared to the size of the planet. And so we're going to look at some problems in a minute that will make sense. Okay, so here is on your notes, here's the picture I just told you, just a miniature, and then here's a neat little cartoon that I found that shows our solar system in terms of gravitational or potential wells. Way down here is the potential well created by the sun. It's too big to show on the scale. We see that Jupiter has a huge well because of its large mass, Saturn slightly smaller, Neptune nearness out here, and then we see the tiny little wells created by, I can't read these, but Mercury, Venus, Earth, Mars, etc. Okay, so the idea is if we want to escape, I think this is Earth, I can't really tell. If we want to escape Earth, we just got to get out of that little hole, and when we're out of that little hole, we're still in the big hole created by the sun. So if we want to escape the solar system, we got to get out here. If we get too close to Jupiter, we're traveling, then we fall into its hole and we need enough energy to get out of it. So what we want to look at is how do you escape a hole? That's called escape velocity, and that's really the biggest solution that we want to come up with to this idea. All right, so let's look at 2 problems and we'll finish. All right, so let's revisit the idea of what is the potential energy of an object near at the surface of the Earth, okay? And we got to look at this in a more universal sense. In other words, if I say, okay, well, I say I'm standing on the ground, what's my potential energy? And you wanted to use the old equation, mgy, well, you'd say, well, why 0? So we have no potential energy. And I guess that's true relative to the surface of the Earth. But what if we want to understand, again, using, I'm going to go back a second. Right, so this is the surface of the Earth, right? So relative to the center here, we have 0 potential energy. But now I'm talking relative to infinity. How big of a hole are we in by standing on the surface of the Earth? That's what we're asking for here. So it's going to be non-zero. It's going to be less than 0 because it's negative, but it's still going to be a numerical value. Okay, so if we use our universal gravitation, or universal gravitational potential energy, we have negative GMM all over R. Okay, so if you recall, that's 6.67 times 10 to the negative 11th. Mass of the Earth is 6 times 10 to the 24. We put in a 1 kilogram object, and then we have to divide it by the radius of the Earth, which is essentially 6 times 10 to the 6th, okay? So we punch those numbers in your calculator, and you get a surprising number. It's a pretty big number. It's negative 6.7 times 10 to the 7th, all right, joules. All right, so we are in a pretty deep hole being at the surface of the Earth. We are talking about almost 100 million joules of hole we're in. So that is quite a big hole to get out of if we want to leave the Earth and not come back in. And that's a solution we'll talk about in a minute. Now, how would this change if we moved one Earth radius above the surface? So if we got further away from the Earth, so right now we're on the surface right here, if we're up here, what would we expect about the potential energy? Well, we'd expect it to get weaker. We'd expect it to get less negative, and we'd expect it to increase, because to pull an object away from something that's trying to attract us, we expect it to go up. So I take that back. We want to say it's going to get weaker. It's going to actually increase, but it's increasing towards zero. And that's kind of a weird way of looking at it. Okay, so it would increase by a factor of 2 because we're decrease. Oh my goodness, sorry. It would increase, okay, by a factor of 2 because we're twice as far away. All right. Now let's move on to this. How would this object escape the well? Okay. In other words, we would want to be able to be moving such that if we were to turn off any engines that were forcing us, we wouldn't fall back into it. So imagine you were literally in a hole. You had to jump out of that hole. You couldn't necessarily climb out. How much speed would you have to have so that you could get to above the surface or at the surface of the hole you're in and land on the ground and not fall back down? It's kind of a similar problem. So rather than look at force and acceleration, we want to look at energy. So we're in an energy well, a potential well, so we want to give it enough kinetic energy. We want to be moving fast enough, give enough speed, such that UG is 0. Okay? In other words, when we're at a potential energy of 0, we're out of the hole. And that we know is at infinity. Okay, so that's going to help us in our solution. So we're going to use conservation of energy. So let's say we're starting right here at the surface of the Earth. We want to start with enough kinetic energy to overcome the potential energy that we're already in, right? When we're by the surface of the Earth, we have a potential energy, and we want it to equal a new kinetic energy prime plus an old, the new gravitational potential energy. Okay? Well, at the escape, this is going to be 0. Okay? That's by definition, we've escaped it. And we want and if we're at 0, we just got enough energy so that our kinetic energy is 0. In other words, that's the threshold. We gave it enough initial kinetic energy that when we landed, or not landed, but when we got out of the hole, we are not moving anymore. Any extra kinetic energy, we'd be moving with extra speed. So essentially, the solution is that if you want to escape a well, you set the kinetic energy initial to whatever well you're in. Okay, so it's going to equal the negative of our potential energy. All right, so I would say 1/2 mv squared. We're going to call this v escape now, is going to equal negative of the negative, so g m all over r. Okay, so if we do the math, right, the little m's cancel out, we end up with a nice little equation that says the v escape velocity for any planet is equal to radical 2 big G m all over r. And that's a really useful equation for problems to solve. So we can now, in the minute we have left, let's apply that to the Earth. If we want to escape the Earth, how fast would we have to launch an object? Okay, so it would be, V would be equal to radical 2 times 6.67 times 10 to the negative 11th. Mass of the Earth is 6 times 10 to the 24. It's a big radical sign. All over 5.96 times 10 to the 6th. And that is going to equal the value of 11,600 meters per second. So if we want to send a probe to Mars, to Venus, not to the moon, moon is still in the hole, well beyond anything in our solar system, we have to fire it with at least a speed of 11,600 meters per second. Okay, so we'll do some other problems together as a group. If you have any questions, make sure you note them and ask them in class.